Okay guys, here's our final part of the X-ray circuit. Chapter 4, I told you this in the very first recording that I made, that this was going to be a long chapter. It is. It's a lot of information. The good news is every bit of this is useful information, and I think it's things that you've heard about in the past. So now just putting them all together. So we have already gone through all of the principles of electricity, and then we talked about transformers and generators, and then we also talked about electromagnetism and how these two things work together. Now we need to look at the X-ray circuit itself, the X-ray unit, how it works, how we choose things to make our exposures. Now this is that one picture again that shows the auto transformer that's here in X-ray. So this is the auto transformer, and that is the most important transformer for an X-ray circuit. And this transformer operates on the principle of self-induction, as I talked about earlier. Now, why did I go through the whole thing of mutual induction and self-induction? Know the difference between them, but the more important thing is that if you see a question, the auto transformer in an X-ray circuit works on self-induction. This transformer has only one coil of wire, and it's around a central magnetic core. Do not think that this is the shell type, which has two coils of the wire. It's just one. That one coil is used as both primary and secondary, and the outside wires are attached at different points along the coil, and the induced voltage varies depending on where the connections are made. But those connections are also made by you, the radiographer, okay? So keep in mind this auto transformer and how important it is. Now let's look at the entire X-ray circuit. Here is just a simplified view of the general X-ray circuit, and it is a simplified version, but it's what you need to know to understand the principles of operation. I can tell you, you'll see this picture on tests, not only in this course, throughout the course, in some of your other classes, and then I should have said through the program. You will see it on your review, and then you will see a question on your registry about this. It'll have this picture and then an arrow pointing to something, and you need to know what that is. So by doing that, you need to know first off that it's divided into three sections. One is the primary circuit. Now this one is at a different kind of angle than the rest of them are, but it gives you an idea. So the primary circuit here is in orange, and then we have the secondary circuit, which in this picture is blue, and then the filament circuit, which is on the bottom, which is, I guess you can call that pink. It's supposed to be kind of purpley. But the difference is you've got to know exactly what each one of these circuits involves and what it contains and how one can't work without the other, okay? So let's just get started. The primary circuit consists of the main power switch, circuit breakers, auto transformer, timer circuit, and the primary side of the step-up transformer. So if we look right here, there those things are. So here's the power supply, circuit breaker, main power switch, auto transformer, and I've already pointed out that's the big one that you'll really need to know. And then here's the KVP meter, the exposure timer, and then the step-up transformer. The secondary circuit is the secondary side of the step-up transformer. Then you have the MA meter, a rectifier bank, and the X-ray tube, all except for the filament. So right here, so here's your step-up transformers. So this is the one side, primary side, secondary side. These are your rectifiers on both sides here, and then here's the X-ray tube. Notice here though that only part of this is blue for the secondary unit, and the other side is part of the filament of the X-ray tube. So the third part is the filament circuit, which has a rheostat, a step-down transformer, and the filaments. I'm going to go over each one of these individually and separately because you need to know what each circuit has and what each of those components does. So here's the filament. So there's the filament in the tube. Here's your step-down transformer and your rheostat. And then if you notice, it also kind of is connected to the auto transformer, but not because this goes that way. It's when this is done, it lets the primary know that exposure is done. We can move on with the next one, okay? So here's our primary circuit again. Now, I want you to look at main power switch. Now that is not going to be at your console. This main power switch is in a generator box somewhere over in another area, but that's connected to the incoming power supply. And then you have a circuit breaker that's built in. This is not something you would touch, because if it trips, then you have to have other maintenance coming in. Then you have, here's the incoming power supply, there's your main power switch, there's your circuit breaker, here is the auto transformer, I keep pointing out, here's the timer circuit, or the exposure timer, and then the primary side of the step-up transformer. I want you to also notice right here you have a kVp meter, and it should be listed, but it's just part of the primary circuit in general. So let's know all of it, and let's go on. Oh, main power switch, incoming power supply, circuit breaker, auto transformer, there's your timer, and there's your step-up transformer. Sorry, I was supposed to be clicking those arrows as I taught, but you've still got it. You've got the idea. So you have one of these available, and if not, I'll just stick another one out there on the web. I want you to print that as many times as you need to. That's blank, so that you can write in where all those areas are. So the primary circuit, if you start at the beginning, the main power switch is an on and off switch for the unit connected to the power supply. Because the incoming power is not consistently 220 volts, you have a line compensator. And that is usually wired to the auto transformer, and it automatically adjusts the power supplied to precisely 220 volts. Now, in case you didn't know anything about electricity before now, when electricity comes through the wall, that doesn't always mean it's a steady. It's a whole lot better than it was, say, even 30 years ago. But that line compensator is there just to make sure that we get exactly 220 volts. The circuit breakers are also included here to protect against short circuits and electric shock. So if any of you have been in the medical field for any reason, anytime you go to a facility, they have what we call red plugs, and those red plugs are probably in other businesses too, but in the healthcare facility, they're even more important, because what are we dealing with every day? We have patients who don't need their machinery to go down. So whenever you do a red plug for your machines, that means that it's connected to the generator. If you're working in the middle of a storm and the electricity goes out, those red plugs, number one, they have a circuit breaker in there so it won't fry your machine, but it also means that once the generator kicks in, you can still use that piece of equipment. Okay, so all of these things are in part of the primary circuit because that's the main power. So the other parts of it, we've already talked about the auto transformer, but it is an adjustable transformer controlled by the kVp selector on the operating console. When you select a kVp setting, you control that transformer. And as we talked about earlier, the transformer operates on the principle of self-induction. When you select a kVp setting, you are determining the number of turns on the secondary side to be included in the circuit element and the output voltage. Because of its function, the auto transformer is sometimes called the kVp selector. So when we looked at that picture before, that's why that's also there. So here, let me just go back there real quick. When I say the kVp meter, it's really not, but that could be called the kVp selector. But it's still the auto transformer because that's what you are selecting with it. Its primary purpose, the auto transformer, is to provide voltage that will be increased by the step-up transformer to produce the kilovoltage that you select at the console. So coming in power, or the incoming power, is 220 volts. That step-up transformer increases it to ever how many thousand volts that you need to take an X-ray. The step-up transformer increases the voltage to the necessary kilovoltage for X-ray production, and that is the dividing line between the primary and secondary circuits. So you need to understand that the step-up transformer actually has two parts. So you have the primary part and then the secondary. That's why they're called the secondary circuits. Unlike the auto transformer, the step-up transformer is not adjustable, and it increases the voltage by a fixed amount so that it can create an X-ray. The timer circuit, or the exposure timer, is located in the primary circuit because it's easier to control a low voltage than a very high one. And there are several different variations, okay? Some of the variations include a synchronous timer, okay, and that is based on a synchronous motor. And I don't know if you know what the word synchronous means, but it means that at the same time. This motor is designed to turn a shaft at precisely 60 revolutions a second. It turns a disc connected to the on and off switch, and then there's some gears in there, and the exposure time selected determines the reduction gear used. Therefore, the time it takes the disc to move from the on to the off switch. So just know a synchronous timer, and then there are also electronic timers. So the second variation, the electronic timer, is very sophisticated, but it's more accurate. And it's the one that we use more often today. So hint, hint, you need to know that. This timer is based on the time it takes to charge a capacitor through a variable resistor. Yep, big words for electricity. Once the capacitor receives its pre-programmed charge, it terminates the exposure. And that time that it takes to change or to charge that capacitor to its pre-programmed level is controlled by the variable resistor. And therefore, if we can achieve a 1-second exposure, then the resistance is increased, so it takes longer to charge it. And what do we actually work in? I've said it, but you haven't actually gotten to use one yet. We work in milliseconds exposure. So there's virtually no resistance. The capacitor charges very quickly. The timer terminates the exposure. This is one application for a resistor in the X-ray circuit. The mass timer is a variation of the electronic timer, but it monitors the current passing through the X-ray tube, terminates the exposure when the desired mass is reached. And because of the way it functions, this timer is actually located in the secondary circuit instead of the primary circuit. So we more often use an electronic timer, and that is actually in the secondary circuit, but you need to know about the other timer too, because it just depends on the equipment that you have. Now, serving the same role as a timer is something called automatic exposure control. You will hear from here on out that's just called AEC. So your AEC device operates a little different from the others because it uses the patient's body part as the variable in determining when to terminate the exposure. So when we talked about the electronic timer, that's what this is about. But when you have AEC, and all of the new machines do today, you first need to make sure that you have chosen the right cell that you're going through that body part, and you'll talk about that more in your next quarter when you get into anatomy and you start talking about how you actually take an X-ray. But when it goes through a body part, you have already selected, is it a small body, a medium body, or a large body, so that it has a little more power to begin with. And once it reaches that little sensor in the bucky, then it will turn it off. And that is a device called the ionization chamber. That ionization chamber is a radiolucent device that's placed between the patient and the image receptor. And when the X-rays interact with this chamber, its atoms are ionized, creating an electric charge. That charge becomes a signal that terminates the exposure. The AEC can be adjusted so that more or less of a charge is needed before it terminates. AEC calibration is performed by installation personnel. That means whoever put in that piece of equipment. They use phantoms, usually out of acrylic or something like that, and they determine with the different types of thickness on those phantoms what it needs to be set at. So that's not something that you would do, but you may sometime be asked, how is AEC calibrated? And that's upon installation, and then your QC, as it moves forward, they will check that every so often. And the amount of exposure varies with the image receptor, and it'll have to be recalibrated if anything changes. So when we went from film screen to a type of digital, which was CR first, a cassette-based digital, then they had to recalibrate. But you can still use the same equipment. Then when we went to full digital or DR, that's direct radiology, they had to do it again because it's going through less materials to get there. When your x-rays pass the patient or exit the patient, and we call that remnant, they have to go through that ionization chamber. And then the length of exposure is determined by the thickness and density of that patient's part, and so it makes a difference. So I just want you to get this in mind. I know this is a long time talking about this one subject, but it's very important. When you use AEC, think about having an infant, say a 9-month-old, and then a 40-year-old average-sized man, and you were to do an x-ray on both of them. You could basically choose the same exposure for both, but which one is going to hit the timer quicker, or the ionization chamber quicker? The infant. Because of the difference in the thickness and the density of these two patients, it takes longer for x-ray to go through that larger person to make the signal on the chamber to cut it off. So that's why this is very important, and that's why it's on the primary circuit, because all of this has to do with making that initial exposure. So to this point, the radiographer, you have selected the exposure factors, your KVP and mass, along with all other factors. You've pressed the exposure button. I can't say that right. In the primary circuit, this results in a voltage being determined by the auto transformer. It's applied to the primary side of the step-up transformer, and then a voltage is selected from the auto transformer and applied to the filament circuit. Therefore, the stage is set for the rest of the circuit. With the voltage and the current selected and traveling, now you're going to actually get an x-ray production. So primary circuit involves you selecting these two plus whatever other parameters need to be chosen, and then you get started. So now let's look at the secondary circuit. The secondary circuit consists of the secondary side of the step up, so there's the blue side, the milliampere meter, which is right in that particular area, a rectifier bank. Now I want you to know there's two of those. So notice there's one on top and one on bottom. And then the x-ray tube itself, but only the blue part of it, the tube side, not the filaments. So when you look at the secondary circuit, it appears there's less there, but the most important ingredient of this side is the rectifiers. And so we're going to talk about that a little more in detail. The secondary circuit begins with the rest of the step-up transformer, and the role, we've already talked about why that happens, but the milliampere meter, or the MA meter, is a device placed in that secondary circuit that monitors tube current. The rectifiers are needed to convert AC to DC, and we're going to have to talk about that a little bit more. In general, AC, alternating current, is necessary to operate correctly. However, to allow the tube to be exposed to alternating current would just be disastrous. So it needs that direct current first, and then, it gets alternating current and has to transfer it to DC. So within the X-ray tube, current must always flow from the anode to the cathode side, and electrons from the cathode to the anode. We talked about all that in Chapter 5. So in order to convert that alternating current to direct current, we use rectifiers. So let's bypass the circuit for just a little bit and let's talk about just the rectifiers in general. To be used most effectively, rectifiers are arranged in pairs. So if you know anything about alternating current, it has an open path in each direction. And it's possible to use only 2 rectifiers, but then that suppresses or wastes the negative half of the cycle and only protects the tube during that phase. So one half of the alternating current cycle flows through the X-ray tube and the other half is going the wrong way, or it's blocked. And this type of waveform is called half wave rectification. So here's the alternating current. So some is above the baseline, some is below. And when you have half wave, you have taken out this on the bottom, but that means you don't have a full supply of radiation. So this figure shows AC on the top and what the waveform would look like with only 2 rectifiers. So we're only fixing the bottom part of that alternating wave. But the reason we have it in pairs is so that we can have 2 of them. So we have one up here and one here. That means we have 4 rectifiers in use and full wave rectification is achieved. Note the arrangement of the 4 rectifiers in this figure. They're highlighted to show the ones in use and each keep half of the cycle. So I put the other arrows here, but if you look, here's a red, there's a green, and there's a green. And that's what it's doing, is correcting that alternating current. Through this, it's necessary to route it through the tube correctly because the tube, except for the filaments, is part of the secondary circuit. And because the tube head assembly is the subject, and we've already covered that in Chapter 5, then it is addressed in detail here. So here's just our secondary circuit. There's our second part of the step up, and then these are the rectifiers here, and they are needed to change the alternating current to direct current. Now, what we taught here, I'm going to back up just one. This was half wave rectification. We've only cleaned up the bottom. But if we put 4 rectifiers instead of 2, now we get full wave rectification. So 2 of the rectifiers take care of the negative half, converting it to full rectification. And now they take advantage of the full wave, and it's much more efficient. Because now if you're getting the full if you're getting the full wave, you've got more power coming in, so you don't have to use as much power to try and create the X-ray. Ripple is the variation of the DC voltage within a power supply, and it's coming from the AC source. And that ripple is because there's complete suppression of the alternating waveform after rectification. Ripple voltage originates as the output of a rectifier or from the generation and communication of DC power. If you have a standard 60 Hertz generator with 60 Hertz of incoming power and it's fully rectified and then gone through a capacitor bank where it's smoothed, then there is near constant potential provided, and that is what you want. You don't want to try and take an X-ray where you've got bursts of electricity. You want constant potential for that X-ray to be made. So at the console, when you press the exposure switch, you're sending a voltage to the step-up transformer to increase the kV. Then that kV is passed through a set of rectifiers so that it travels through the X-ray tube correctly. So this is a little bit better, and I guess I should have been pointing that out as we did it, but here's a full wave rectification circuit and it has 4 valve tubes. Here's the primary side. So we send in 120 volts of AC. Now we're going to the step-up transformer. Now look, on the secondary side, now we have 60,000 volts because it made what you chose to do. So that would be 60 kV. And then this rectification is making sure all of that kV is usable and there's not some on the bottom of the waveform. So then it sends it to the cathode and anode. Here's our X-ray tube. Now, once it's come here, we're going to go into the filament side, and then we'll talk about how it goes step down in the filament side, just so that it goes back to kind of normal X-rays, electricity again. But that's the whole purpose of full wave rectification. So that's a cute little diagram right here. Now let's look at what our book tells us. The rectifier that we use more commonly in today's X-ray circuit is a solid state rectifier. Now, do you need to know this completely? No. What you do need to know, though, is that we use a solid state rectifier today. Okay? It's made of two semiconductors, and they're crystals. One is a P-type, so there's your P, and the other is an N-type. The P-type has an abundance of electron traps, where the N-type has an abundance of freely moving. So, and you've noticed here's their positive and negatives. And these two crystals are joined to form a solid state diode. And what happens here is when a positive charge is placed on the P-type crystal and a negative charge is placed on the N-type, then it conducts electricity. Okay, so it always has to move from the anode to the cathode, and it is going to conduct. To do this, both the traps from the P-type crystal and electrons from the N-type crystal move toward and across that junction to allow current to flow. When the AC cycle reverses and the P-type receives negative and the N-type receives positive, it will not conduct. And that's because it traps the electrons and they stay at home. They do not move to the junction. So this is another image in your textbook, and it's talking about conduction and non-conduction. And note the change in polarity in each half of the illustration. So if it travels from here to here, so there's positive, they conduct. Here it does not conduct because that has now become negative and positive, okay? Don't worry about the image itself, but remember this symbol? That means something, and if you go back and look at your other symbols in your book, but know that we use solid state rectifiers in today's X-ray. So knowing that with the solid state rectifier, let's look at the different types of current that you could have. For rectifiers arranged in this way, both halves of the AC cycle are used, and the resulting waveform is illustrated here. So now, remember in before you had that blue was on the bottom of the line? Well, now it's moved back up here, so we've rectified, but it's still, this is a single phase generator. So I'm throwing in something else for you to try and understand, and that's with the generators that are used in X-ray machines. So the energy fluctuates from 0 on the line to the maximum voltage peak of the wave, and that's called ripple. But if you have a single phase full wave, so that takes a while, single phase full wave power, you still get 100% ripple. What that means is that it's always something fluctuating. Now, these are our generators and X-ray machines of the past, and that's why we had to use precise exposure factors to get them. There are not very many of these still out there with the single phase generators, but this is thrown at you here just so that you understand. You can have a question that asks, if you have a single phase full wave rectification unit, how much ripple would you have? Your answer should always be 100%. So when it's single phase, it doesn't matter how much you've rectified it, it's still going to always have that loop like that. So although single phase full wave power is much more desirable and less wasteful, it's the ripple that is the problem, because our X-rays vary in energy already from our kV, and so if you have that ripple, that also means it's not getting all of the energy that it should have gotten when you selected it. But there's you an example of it. Now, a solution to single phase full wave is to use 3 AC waveforms at the same time, and this is called alternating currents, or a 3 waveforms. So single phase, full wave. Now we have three waveforms and we synchronize them. So with a little bit of engineering and electricity gurus, three waveforms can be phased or synchronized. Each is generated independently, and then they're phased so that each one is 120 degrees out of step with the next. The result is a waveform shown like this. So you can see the three different colors. So here's the red one, here's the purple one, and here's the orange one. So they're all starting, but look, they also start overlapping, so you have a little bit more. So that's still three single-phase waveforms, but they are unrectified, but they are synchronized, and so they're alternating currents. Okay, so that's just a different way to do it. Now, if you have a three-phase full wave, it'd be a terrible waste not to rectify those alternating waveforms. So instead of this, where it's still on the bottom, now we're going to rectify them all, and we select them just like they were single phase, and now the tube sees a waveform like the one in this figure. So notice how all those waveforms are all above the line and they don't come back down. So that means, so let's see if we can go back here. So what it's done is taken this and this and this and then scrunched them all together, so now it looks like they're all way up here. This is referred to as three-phase power. So instead of a single-phase generator, we now have a three-phase generator. There's less ripple than the single waveform, but there's still some ripple. So depending on the number of rectifiers and the engineering, it can have anywhere from a 13% to a 3.5% ripple. And so we want the least amount of ripple to have a good image. So a 13% ripple is going to happen when you have a three-phase 6 pulse. So you have 6 of them all thrown out there at the same time. The 3.5 is a three-phase 12 pulse. So as you notice, the more pulses that you can get to interact like this, see, that's just 3 waveforms, or 3 waves. Here's a 6 waves, or 6 phase, and then a 12 phase, and it decreases the ripple. So let that sink in a minute. This means X-rays produced now have anywhere from 87 to 100% of the selected kVp in an 6 pulse. So in this 6, you could have as much as 13, but you could have as little as 0. So you could actually use at least 87% and almost 100% if you have 6 pulses. But if you have a generator that has 12 pulses, then that 3.5 goes from 96.5 to 100%. So by using more pulses and the 3 phases, trying to alternate these currents, you can get less and less ripple. Okay? So know that if you ever see a question, the ripple that could occur with a 3-phase 6 pulse generator, you need to remember that that can be 13%. That's the ripple. This is how much of the kVp it gets. With 13% ripple, you get 87% of the kV you selected. Now, again, it can go to 100%. It just depends on the X-ray. It depends on a whole lot of other factors. But it can go as low as 87. But if you step up to a 3-phase, 12 pulses, then the most ripple you'll get is 3.5. So that means the lowest amount would be 96.5. So make sure you understand those differences. Here, they can be phased or synchronized, and here is what happens the more phases that you get, so, or pulses. So it's still 3-phase, but now I have 6 pulses instead of 3 pulses, or I have 12 pulses instead of 3 pulses. Okay, so translating into what can actually happen, the next evolution to improve this is the use of high-frequency generators, and this is the statement you need to know. With high-frequency, full-wave rectification, you have less than 1% ripple. So the standard 60 Hertz incoming power is fully rectified, sent through a capacitor bank, and it smooths it out, and then there it chops that DC waveform and converts it to high frequency alternating. And this low voltage high frequency is then passed through a step-up transformer that converts it to high voltage AC. It goes again through rectifiers, that's why we need all 4 of those, and where it's moved to provide with almost constant potential voltage waveform. And these high frequency full wave rectifying generators produce an X-ray tube with less than 1% ripple. So this figure is demonstrating the resulting waveform. These are usually smaller, lighter, less costly generators, and they offer better exposure reproducibility. So people should move up to them. The problem is when people have older equipment, they keep it because it's still working, but it may not be as efficient and they just don't want to spend the money to get something new. But when it's time to get something new, just think about it like your iPhones. If you were on an iPhone 5, but you finally need to replace it, but we've already got an 8 out, or 10 if you want to go that high, but you wouldn't, if you could afford it, you'd go on up to the 8 and get the best that you could rather than just getting another 5 just because it could do it. So if that didn't make any sense, I apologize, but I want you to know that the differences in our generators are single phase that can have up to 100% ripple. We can have a 3-phase 6-pulse that has 13% ripple, or a 3-phase 12-pulse that can give you up to 3.5% ripple, or you can have a high frequency full wave rectification with less than 1% ripple. And if you ever see these pictures, you should be able to see what they actually stand for. Okay? So, in the secondary unit, or the secondary circuit, at the console, you press the exposure. You've already sent a voltage through the step-up transformer. It has increased the kV. Now it's passed through a series of rectifiers, so it travels to the tube correctly to produce an X-ray. Now there is a large positive charge that resides within the anode and a large negative charge on the cathode, which is where it's supposed to be. The only thing that's lacking is the source of electrons, because how do we actually make an exposure? You have electrons that are boiled off through something called thermionic emission. That begins us with the filament circuit. So, primary circuit is mainly for the on and off and to get the selected kVp and current. Then your secondary circuit actually makes that kV happen, rectifies it so we have enough energy to produce, and now we're looking at the filament circuit. So right here is the tube with the filament, and this is the filament circuit, and then this is a step-down transformer and the rheostat. Those are the 3 things. So you have rheostat, step-down transformer, and the filaments. But remember the cycle. We started here, around this way, okay? So that's how it works. The rheostat is what begins with the filament circuit. Now, you would think it'd be the other way, that it would come from here to here. No. At the same time you make this exposure, this is happening and this is happening. Okay? Just so you understand that. The rheostat is a variable resistor controlled by the MA selector on the operating console. So, at the primary circuit, where you make your decisions, the kVp goes this way, your mass goes this way. Because why? This is the energy needed for the X-ray to go through the patient. This is the amount of X-rays that you're going to use on your patient. The milliampere parameter is called tube current because it reflects the rate of flow of electrons passing through the tube during an exposure. You, the radiographer, adjusts the milliamperage on the operating console, and by doing that you have adjusted the rheostat, creating the amount of resistance in the filament circuit. You have ultimately created the number of electrons, or the filament current that you are going to use, the higher the milliamperage station number, the lower the resistance. So a 100 mA station will have very little resistance to the flow of electricity, whereas a 1000 mA station has very little resistance, whereas 100 mA will have considerable resistance. So you do want the highest mA possible with the lowest time. So here's another reason. Not only is it good for your patient, but it's also good for your X-ray equipment. So remember, the rheostat is what you're selecting your MA. Okay, it should be noted that the exposure timer works in concert with the rheostat, and that rheostat controls filament temperature and the rate at which electrons are boiled off of the filament. The timer determines the duration of this process. Together they determine the quantity of number of electrons that are boiled off and available for X-ray production. Okay, so the exposure timer and the rheostat, where MA and time determines the quantity that are boiled off for X-ray production. You have a step-down transformer here to increase the current by reducing the voltage that's applied to the filament. And the purpose of the filament circuit is to control the degree and duration that the filament is heated, which in turn controls the number of electrons that are boiled off that ultimately become the tube current. Although the step-down transformer reduces the voltage applied to the filament, we're not concerned with the current through the filament. We talk about the output current of the transformer, and that as voltage decreases, current increases. So you remember in part 2 when I talked about the number of turns? So the number of turns and your kV are always directly related. The number of turns and your current and the number of turns and your resistance are always inversely. Okay, so keep those in mind. That's why I went through the electricity part before we got to here. The final piece of the filament circuit is the actual filament. These are those tiny little coils that are in the cathode of the X-ray tube. If you can see right here, these little coils right there. And you select the one that you want by selecting large focal spot or small focal spot. When you select one of these, then you are selecting the filament that is heated and used for the exposure. So seeing these up close and personal, and these are magnified, there's our large focal spot and there's our small. See this difference in sizes right there. So that's the whole point of the filament circuit. The goal of the filament circuit is to literally boil electrons out of the filament wire. Normally, a large filament current of 5 to 7 amperes is required to produce a tube current in the range of milliamperes. The thermionically emitted electrons are needed for X-ray production and represent one more step in the manipulation of electricity. However, in the filament circuit, we're boiling these electrons off of a very small wire, and we must precisely control the current that is applied, because if the current is too high, it's going to kill that little bitty wire right there. So that's why we have to have a step down to be able to take care of that additional information. Okay, so now at the console, within the filament circuit, when the exposure button is pushed, a voltage and a current is sent through the filament circuit. Quantity is controlled by the rheostat that reflects the MA that you've already selected. The step-down transformer reduces that and increases current. It heats the filament chosen and begins boiling off electrons. And then the time you have already selected controls the duration that the voltage and current in the X-ray tube is applied. That's a lot of work, but the time selected by you controls the duration, and then that's described when we talked about either the synchronous timer or the electronic timer, which are then basically broken down into your exposure factors. All right, Now that all the pieces and parts have been covered, let's walk through the X-ray circuit again and pretend from the beginning to the end. Now, we've already covered the tube itself in chapters 5 and 6, so now you know how it's being produced. So number one, the main breaker. That's where alternating current comes from to power the entire circuit. The exposure switch. You push the button to start an exposure, which closes to start the exposure. Remember, if it's open, the electrons cannot get through. So when you close the circuit, X-ray can come through. Auto transformer is where you adjust the kVp. Your timer is the part of the circuit that stops the exposure, so like your backup timer. Your high voltage step-up transformer, this bumps the voltage so that the X-ray tube has high voltage to make electrons and they have enough energy to form an X-ray. Because if not, you've just got electricity. So all this right here has been primary circuit. Now the step-up transformer has a secondary side, so now we're going into the secondary circuit. Then we have the rectifier, a 4-diode rectification circuit, making the current go in only one direction. Then you have a filament circuit variable resistor. See, there's not that much in the secondary, okay? This variable resistor adjusts the current going to the filament, and it's going on at the same time because it's over here in the bottom of your image. And it adjusts the current, and then you have your step-down transformer, and this is what steps the voltage down, creating the ability for the current to go up. The tube itself is where the X-rays are created, while the rotor stator is rotating the anode. So that is the entire way that it works. The appropriate place to begin is the operating console, just like in an automobile. Options and arrangement vary. If you go to 3 different clinical sites and they have 3 different instruments, they all have the basic options in common. The operating console offers options for selecting your kVp, MA, exposure time, and focal spot. Those are the 4 factors you can actually decide on. If the unit is equipped with AEC or anatomic program, and we'll talk about that in another whole discussion, those options are displayed. And that's back to the varied pieces of machinery. The same is true for Bucky selection if both a table and a wall Bucky are available. So, you have to decide, are you taking an X-ray on the table or standing up over at the wall? The process begins when the radiographer selects an exposure technique, which specifies kVp, MA, exposure time, and focal spot. And then from here, it's easiest to follow the sequence events in 2 parts. This discussion follows voltage through the primary and secondary circuits, then follows current through the filament circuit. The kVp that you select adjusts the autotransformer, determines the number of turns on the secondary side that will produce the voltage through self-induction, because it's a autotransformer, that will be sent to the step-up transformer. Then the step-up transformer increases the voltage by fixed amount through mutual induction to produce a kilovoltage selected on the operating console. And this transformer represents the transition from the primary to the secondary circuit. Once kV is selected, it must be rectified for the tube. Where the X-ray tube is concerned, the electrons must always flow from cathode to anode. Solid rectifiers are used to route electricity through the tube correctly, and then the number of rectifiers used depends on the circuit type. These one-way valves route current from positive to negative and electrons from negative to positive. After passing through the rectifiers, electricity creates a large positive charge on the anode and a large negative charge on the cathode. Cathode has what? Focusing cup. Focusing cup is the part of the tube that surrounds the filaments. Then we return to the autotransformer to cover the other half. The filament draws electricity from the autotransformer, sends it to the rheostat. The rheostat is a variable resistor controlled by the MA selector on the operating console. Okay, and that rheostat is part of your selection along with the focal spot selector representing the two filaments, a large or a small. When the MA station was selected, the appropriate filament was also selected, and then that sets the resistance in the filament circuit. And now it's tied to the focal spots. So from that rheostat, electricity travels to the step-down transformer. And recall, we're more concerned with the current output than with the voltage. And as voltage decreases, current increases. Inverse relationship. That adjusted current from the step-down transformer then travels directly to the filament within the focusing cup of the X-ray tube. And that current heats the filament to which electrons are boiled off in a process called thermionic emission. So that's how the X-ray circuit works. Your X-ray production we've already covered, but just to remind you, a group of electrons is created by the filament. The kilovoltage applied to the tube creates a large positive charge and a large negative, so we've already said that. And then large positive charge attracts the electrons that are boiled off. Opposites attract, and in that 1 to 3 centimeter gap between the cathode and anode, the electrons from the filament reach speeds of about 1/2 the speed of light. The large negative charge on the cathode keeps the electrons crowded together, and then the electrons travel across to the anode and interact to produce X-rays until the timer circuit terminates the process. That's a long, I don't even know how to say it, words to say how this actually happens. So you need to be able to follow from the beginning of the exposure, the on and off button to the exposure switch all the way to where X-rays are made. So guess what? We made it through. So now we have covered nature of electricity, potential current resistance, conductors and insulators, electronic devices, magnetism, electromagnetism, electromagnetic induction, basic generators, motors, transformers, and then we talked about the X-ray circuit as far as the primary, the secondary, and filament circuits. You can now explain the role and function of each part of the X-ray circuit and how the basic principles of that circuit create X-rays. I don't want you to get so overworked with this information, but I do need you to know the basics of everything that I talked about. Make sure that you understand and know the definitions for all those parts. What is electrostatics? What is electrodynamics? And there's a whole million other things. Hopefully just listening to me so you can understand and read your book a little bit better will help. But I also want you to remember, just like in this picture, we are all one family. And so if you don't feel comfortable asking me questions about what you need to know in this chapter, then at least reach out to one of your fellow students, okay? So until the next chapter, that's it. Bye-bye.